So, good morning again for some of you. Welcome to this online supplement to the lecture in which I explain a bit more about the workings of a computer and the workings of a network. So we were talking about hardware, software, and networks, and I'll try to discuss only the basics. But I think it's pretty useful to learn if you have a little prior experience with it. I think it's pretty important to learn the basics of how a computer works and how computers communicate with each other, and which what we see as the internet network in general, because it helps you understand a bit the issues that organizations encounter, and it helps you understand a bit with the issues that you encounter in your daily use of information technology. So I think it's useful to have at least a basic understanding of computers and networks. So that's why we do this online supplement. So to start with, it's pretty difficult to explain why information technology is important and why you should learn something about that. Because as I explained in the main lecture, IT is ubiquitous, is everywhere. And many things that we use contain some technology, and we don't really realize it contains technology. And on the one hand, that's logical. We, as communications, information science students, and as consumers in general, and people in general, should not be concerned with the technology itself. So we should be concerned in how we use technology, and what are the consequences of technology use, and not about the inner workings of the technology. But oftentimes they intertwine. So it's the inner workings of technology that kind of decide partly what the consequences of the technology are, and that decide and that impact the use and consequences of the technology. So it's useful to know a bit of the workings of the tech in order to understand possible consequences. So in this course, Business, Technology, and Innovation, we talk about technology, but we don't really talk about technology. So we don't deal with many technological aspects, and like I said, we shouldn't. But it has changed in the past, and that makes it more difficult and also more interesting to teach a course like this. On the one hand, it makes it more difficult because we don't realize that we use technology on a daily basis. So much of what we use contains information technology and contains the basic hardware and software that is computer technology. From your washing machine to your camera to your phone to really everything with a chip and a screen, and some kind of interface. But we shouldn't be that much concerned with it, because for us it's about the consequences. On the other hand, it is important. So information technology is important. And why? Well, first of all, because nerds. First of all, because of people like me, and people who work in IT departments, in organizations who do deal with the technology. And they have a very different way of dealing with technology. They have a different feeling about technology. They know the workings of the technology. So for them, so for us, information technology is more about the consequences of how people use it, and for other people, information technology is more about the workings of the technology. So when you work in an organization, you come across people who work in the IT department. So a basic knowledge of how IT actually works, and not only how you use it, is helpful to be able to talk to people who work in more technical departments in an organization. So that's why it's important. Second of all, information technology is everywhere. So like I said, everything we do, everything we use is so much of it contains some information technology. So it is helpful to have a bit of knowledge about IT. Third, because of reason number 2, we are increasingly dependent upon information technology and in general information systems. So we use information technology, but actually information systems, we use them more and more and more in our daily life. So we are more dependent on it for everything. So you see how we shift to online lecturing because of the corona crisis. So we're more dependent on it than ever. So therefore, and it's partly this is supported for a large part because of the technologies that are involved. So we wouldn't be able to teach the course like this in a pandemic 10 years ago. We just had to quit lecturing for a year. But now we can, due to technological advances, due to technological innovations. Well, and finally, if you are able to think a bit about technology in a technical sense, that can cause you to also think about possible innovation. So it's useful to know a bit of technology in order to, to think, okay, what could we do with this in the future? What would the next technology trends be, etc. So basically, information technology is necessary to understand our behavior, how we use technology. It is necessary to understand new innovations in technology, to understand organizations, information systems, social media, etc. So having said that, let's talk shortly about hardware. So what do you need to know about computer hardware? Well, not the inner workings of the hardware. You don't need to know how to make it. But you need to know a bit about what is the hardware exactly. So what is a computer? These are some quotes from people who thought that computers would never be successful. So never trust people who know a lot about technology. Because we've come a long way in information technology. If you compare it to like 50 years ago, and even if you compare it to like 15 years ago, so 15 years before we didn't even have smartphones, well, not smartphones as we now know. And when I grew up, there were no personal computers that we use nowadays, where we had a Commodore 64. More about that in a couple of slides. But basically, what does a computer do? Well, a computer does basically what an information system does. So things come into a computer, then a computer processes that, and then it comes out of the computer. And in the meantime, a computer can store that into memory and then load the information back in order to process it some more and then output it. So it basically means storage means that that processing and output doesn't need to, that input processing and output doesn't need to happen on the fly, but can happen at some later point, or can take some time. But basically what a computer does, it takes input from a user or from another system, it processes that information and it outputs that information. And that's very similar to what I just said in the lecture, what I do. And people who calculate data, so people who used to calculate how planets revolve around the sun, for example, who did other calculations, they used to be called computers. So those people used to be called computers. That was their job description. Because for them, they took input, they processed that, and they gave some output. So they functioned the same as a computer functions nowadays. And that's all a computer does. So this is my mobile phone. Oh, here, my mobile phone. My mobile phone is a computer as well. So if you look at the input on a mobile phone has lots and lots of input channels. So it has a camera here, which is an input. It has a touchscreen, which is an input. It has a microphone here, which is an input. Power for the power cord, USB-C, which is an input. And there are much more. So it has a Wi-Fi transmitter and receiver, a 4G transmitter and receiver, and it has can input if it's straight up or if it's like this. So it has a lot of different input channels. Those get processed, and then it's outputted again also through the screen, to the speaker, to the transmission of a Wi-Fi signal, through an audio signal via 4G. So it outputs that. And that's all a computer does. A computer can only do that, but it can do it very quickly. And of course, my phone has storage. So my phone has a an internal hard disk, a solid state disk in which my contacts and photos, etc. are stored. I had multiple types of storage actually, but I'll come to that in the next slide. So that's basically, you can consider a computer as input, processing, output. And the more you know of computers and technology, the more you consider a computer to be the part that's about processing. So I had a friend who studied anthropology, and he studied how people accepted technology. And he investigated older people, and he asked older people, what do you consider a computer? And everyone who was older, they pointed at their screen. So my screen and my keyboard, that's a computer, because I type something in and it's displayed on the screen. And I know there's a black box somewhere. It was a desktop computer in that time. And that probably does something, but that probably just relays the signal from my keyboard to the monitor. But then when you talk to people, about who know a bit more about technology, they say, no, a computer is actually the black box, because that takes my input, that processes it, that does something with it, stores data, and then it outputs it again. So a bit more in detail. If you look at specifically what a computer does, it has some input devices, what you see here on screen. It has output devices, and then the processing part happens in the middle. And basically, a computer can, well, it does three things. So it has a central processing unit, and a central processing unit is the processor, well, part of the processor in the computer. You know, that's the Intel Core i5 or whatever you have. That's the processor of the computer. And that's the thing that does the calculation. So that takes the input, that calculates it, you know, that does the statistical analysis when you use SPSS, and it outputs it. So that's the central processing unit. So that processes stuff. So that processes information, calculates it and outputs it. Then you have an arithmetic logic unit. It's also part of the processor. And that does actually the core arithmetic in the computer. So that transforms ones into zeros and the other way around. You don't have to remember that for the exam, but just here as a bit of more detail. And a computer has a control unit, and that control unit makes sure that information can flow, or data actually can flow from one part of the computer to another part. So flow from the memory to the processor across the motherboard. That's what the control unit does. And those three parts make up the core of what happens inside of your computer. And you can extend that with a sound card and with a large graphic card, etc. But they also basically fulfill these three functions. Your computer has then two types of storage. It has primary storage, which is called random access memory. That's what when you buy a computer, it says, oh, you have 8 GB of RAM. That's primary storage. So that's the storage that a computer uses in real time to store information for a while. When you turn your computer off, all that information in the primary storage is lost. So that's not stored on a hard disk or something. So that's basically, that storage is the random access memory, RAM memory, which a computer uses to do calculations and puts information which is then displayed on screen, or saves information to use later on to calculate stuff with. That's primary storage. And the primary storage is the random access memory, but there are also smaller primary storages baked into the processor at other locations in the computer. So then you have secondary storage, and secondary storage is secondary storage is your hard drive or your solid state drive or an external USB drive. Basically the things that do not disappear when you turn your computer off. So that's where you store your documents, where you store video, etc. So that's what a computer does. So how do the calculations work on a computer? Well, the only thing that a computer can do is transform a 1 into a 0 or a 0 into a 1. And if you strip everything away from what a computer does, that's the only thing a computer can do. So it can take a bunch of zeros and ones and transform it into another bunch of zeros and ones. And that's it, that's all, nothing more. But a computer can do that a couple of billion times a second. And if you can do that a couple of billion times a second, then you can do a lot of different things. But it basically boiled down to that. So what is the zeros and ones and why? Well, it has to do with how computers originated. So computers were built to store information in a way that you could easily control if the information is there or not. So you can have a switch that is on and off. And computers started out with switches and with vacuum tubes, which had an electron in them or not, in which a current would flow through them or not. So the whole computer systems and the whole all computer systems are based with the idea that things can turn on and off. And it used to be, electrical current and electrical voltage that would dip below a certain point and that would be off and then it would be on. But nowadays it's micro transistors with a very small voltage, and if there is a voltage on the transistor is on and it's a 1, and if there is no voltage it's off and it's a 0, or the other way around. No, I don't think the other way around. And a transistor basically is a very, very small component in a computer, like nanoscale small, that can take an electrical current or shut off an electrical current. And your processor has those, and your memory has those, and it has like billions of those baked onto 1 square inch. So billions of those small gates, which could be 1 or 0. And a computer uses that to calculate. And basically every computer and every storage device you have works like that. So a hard drive used to work with a magnet. So the magnet would be either north or south oriented, so the small magnetic particle on a hard drive. And if it would be north oriented, it would be 0, and south it would be a 1, or other way around. A compact disk works in a way that that when there is a hole, it's 0, and when there is a 1, it's 1, and when there is no hole in the disk, it's 1. Well, actually, not precisely like that, but it's actually, if it goes from a hole to a non-hole in a compact disk, then it's a 1, and else it's a 0. Doesn't matter. It also works with 1s and 0s. So glass fiber, so if you have a glass fiber coming into your home, that works with light signals, and if there is a photon, it's 1, if there is no photon, it's 0, well, it's etc. And we are the ones who set those 0s and 1s. So for example, if I put a pixel on screen, so for if my screen would be only black and white, so if I would have a black screen and I would have 1 white pixel on the screen, then I would turn that white pixel from 0 into 1. So I would give a signal to the computer and would say, oh, well, please, I want pixel number 200,000 to be 1 instead of 0. and then it saves that into memory, and it displays that on screen, and then you see a 1. And when I was young, I had a Commodore 64, and that was still a very basic computer, and you could actually do that. So I could actually give an instruction to the computer. So I could say poke. So I could say poke to a specific location, and when I poked a specific location on the computer, so just like poking it with a stick, so I turn it from 0 into 1, I would get a dot on the screen. So we can set the zeros into 1s, and a computer can also set those zeros into 1s. So a processor basically has a number of things that are called gates, which is the not Bill Gates, but a gate, which are the symbols on the top, and they are gates that automatically turn a 1 into a 0. So, for example, the top left one is OR, so it gets 2 bits, so it gets two 1s and 0s into that logic gate, and it outputs a 1 and a 0. So basically, an OR gate means if you have 2 bits of information coming in, if one of them is a 1, or if both of them is a 1, then the computer outputs a 1. Maybe a bit difficult to understand, but it basically means that a 1 and 0 is flying in from 2 different places, and one of those places gives either a 1 or a 0, and the other place gives either 1 or a 0. And if either the one or the other or both is a 1, then it outputs a 1. And that's an OR gate. And that's how a computer can transform zeros into 1s. And you have to think of a computer processor, the chip, that's the central chip baked in your laptop. You can think of it as a connection of millions and millions of these 8 different types of gates. So it transforms all those 1 into 0s depending on the 1s and 0s coming in. And it does that billions of times a second. And then you get things like Zoom and a video you watch online, statistical software doing stuff. But it basically boils down to that. But there's I'll come to that in a minute, but there are lots of layers building up on that. But there are actually people who work at IBM or at Intel or ASML or whatever. There are actually people who work on such a basic level with computers. So they work with those 0s and 1s and try to make them more efficient. But yeah, enough about this. So this is also the reason that computer language is only 0s and 1s. And that's called binary representation. So a binary representation basically means that your number system is base 2. So we use base 10 as our number system. So we count from 1 to 10 and then we start over again, basically. But a computer counts from 1 to 2, or actually it counts from 0 to 1 and then it starts over again. So if you have 2 1s, so if you have just 1 bit, that can have 2 possible combinations. So 1 bit can be either on or off, 0 or 1. If you have 2 bits, you have 4 different combinations. So it can be 0, 0, 0, 1, 1, 0, 1, 1. So 2 bits give 4 different combinations. 3 bits give 8 different combinations, 2 to the 3rd, well, etc. 8, 16, 32, 64, etc. So oftentimes you come across like weirdly random numbers. So you can only store 256 contacts, for example, in WhatsApp, at least in first versions. I think still, you can only have like 256 people in a WhatsApp group. Those random numbers usually originate because of the 0s and 1s. So you sometimes see that you can only store 512 or 1024 things somewhere, and that's because of the binary system of computers. And that's also what a bit and a byte and a megabyte means. So a bit is 0 and 1. So if you combine 8 of those bits together, so you get a string of 8 bits, like 1 1 0 0 1 1 0, and that's 7, but you know, eight of them together, that's a byte. And a byte has 256 combinations, 2 to the 8th. Then a kilobyte is 2 to the 10th. It's 1024 bytes. A megabyte, 1024 kilobytes, etc., etc., etc. So that's the way that we calculate the storage capacity or the processing capacity of computers. It's all based on those zeros and ones. And like I said, a computer can only transfer a 0 from a 1, or take some input of zeros and ones and convert it into another other zeros and ones, and that's what a computer does. But this kind of shows, this is called Moore's law, and that kind of that law that states that you see that we continue to innovate and innovate and innovate, so we can fit more and more and more information into a computer. So specifically, Moore's law means that we can, so that there's an exponential growth. So this is a logarithmic scale on the y side. There's an exponential growth between the number of transistors we can fit on a square inch of a processor. And you see that runs up to 2018. You can see that we can fit up close to 50 billion, 50 miljard in Dutch, 50 billion transistors, 50 billion of those small machines that can convert ones to zeros. We can fit 50 billion of them on 1 square inch. And that's why computers are so good and so quick right now. And you see, if you compare that to Commodore 64 levels, it's about 100,000 on a square inch. So who cares how many transistors fit on an inch? No, it's important because that has allowed us to do so much more and computers to become so much quicker. Well, let me first explain this one. So this is how computers work on a very basic level. And if you think of computer software, the software that we use is 5, or actually 7 levels on top of that basic workings of a computer. But it all builds up from the ones and zeros. So if you look at, so this is called the layered approach to software and software development. And it basically means that you have people working on hardware and software for starting from the real technical physical layer of the computer all the way up to us being able to do TikTok dances and sending that to our friends. Because it starts with all the basic hardware, so with the ones and the zeros. And then there are people working on the basic hardware and building that. But then on top of that, you have people who make driver software, so who make machine code that can directly interact with the processor of a computer. And that's a language called assembly. So that's really, so again, when I had my Commodore 64 like 30 years ago, I could do that. So I could specifically say to my computer, okay, take the number that is stored, or the 1 or 0 that is stored on this location in memory, then add it to this number, and then store it into another number. so I could really interact with the processor and in my RAM memory with the computer directly.
Your coffee.
Thank you. And that's. My girlfriend even brings me coffee. I'm a very lucky man. Thanks. No, I lost it. Oh yeah, I remember. So, and there are actually people working on that layer of computer hardware and software. Oh. I'll bring you coffee when when you enter the master and we can finally have offline courses again. Remember me. If you remember me and hold me to it, I'll bring you coffee if you're in my master course. I only think. Okay. This is going to be a really strange lecture for the ones who are not following this lecture right now. I'm sorry, there's a chat conversation getting into the way. I'll come back to the lecture right now. So there are actually people working on that layer and working on software development that's really tied to the hardware. Then there are people who work on a layer on top of that. So they are the ones who make the operating software. So they make sure that we can store stuff to our hard drive. They make sure we have a graphical interface to the computer so that we can that we don't see the processor zeros and ones, but we see a nice interface. That's Windows or Apple. Then there are people who work on infrastructure and support software. That's a layer on top of that. So those are the people who build network software, who build databases, who build web servers. And then finally, there are people who build application software. So they build stuff like Facebook, Word, and all the software we use, WhatsApp, whatever software we use on a daily basis. But it all builds up. So I think the most important part of this lecture is to realize that it's not suddenly that we can start using Facebook, but it really has been built up over, I think, 70, 80 years right now. It's been built up from the ground, from thinking about how can ones and zeros interact, to driver software, operating software, etc. And the reason that computers are so easy to use is because there are thousands and thousands of people working on the layers that we never see that are actually there. But it's very important to realize that those layers are there and there are people actually making it possible for us to use simple applications like Word and Facebook. It's all built up onto all those layers you see here on the screen. And that's if you compare it to Lawden and Lawden, to the chapter that they where they explain hardware and software. They say, okay, in an organization there are several parts of the IT infrastructure, and there you see a similar approach. So there are people who are working on making sure our computers work. You have people who make sure the enterprise applications work. You have people who make sure our internet works, who make sure our website works, etc. And all those people work together in the IT departments of organizations or outsourced to in other organizations, who make sure that we can use information technology and that we can use it in our daily lives and that we can study the effects of IT. So I think that's why it's very important to know a bit about all the layers below, right until the zeros and ones of a computer. So that's the basic hardware part. The next part is networks and the internet. So how does a network, how does the internet work? Well, Even if you have no knowledge at all of technology, you realize if you look at your home that you have a Wi-Fi network. There is in a cabinet somewhere with all the electrical stuff in it. There is a box which emits the Wi-Fi signal, and there are a couple of cables plugged into it, and that goes to the internet. So at home you have a network, and your network is connected by Wi-Fi to the central box, which connects to the outside world. Well, that central box is called a router. And that router can connect via Wi-Fi to all your computers. But if you work in an organization or have a very old-fashioned network, or have a dad or a mom who likes to do technical stuff, you may even have cables in your home. So you may even be able to connect with a cable to your computer. Very old-fashioned, but you still can. And especially in organizations, most of the larger computers are still connected via cable because it's much more trustworthy. Those cables are connected. You can also connect the router via cable, and if you want to connect more of them, you can insert a switch. You don't have to remember what a switch is, but this is basically a network. And an organization has a similar network. So an organization has servers, and servers are large computers in which you store central applications. So, for example, Google has like millions of servers which together make up the Google search system, and those are central, bigger computers that only do processing and storing information, but they don't have a direct connection to a person, so they don't have a screen and a keyboard usually. Well, they can, but usually they don't. You can connect one, of course, but they don't. Those are servers. And then when we use an application that is not stored on our computer, that's a client. That's here. So you have different kinds of computers. So you have servers and clients. Let me see if I can give a very simple example. Well, if you store information on Google Drive, so if you work together on Google Docs for your business plan, Google Docs, as you know, is not actually on your computer, so you access it via a browser. So your computer is the client. You only request, can I have this page, and you work directly onto someone else's computer. So you work somewhere on a computer from Google, and on that computer from Google, that is where your Google Doc is stored, and that is where all the processing and all the things behind the screen are done. So your computer is just the interface, and that's called a client. And a server, that's the central computer on which the actual data handling and the processing and everything else happens. And usually, of course, in the case of Google Docs and in the case of Google itself and Dropbox and to other Facebook and other huge applications, it's of course, it's not just one computer sitting somewhere in someone's garage. No, those are huge server centers which are scattered around the globe, and that's what we call the cloud. So this is the image here is an example of a server room. And those data centers are actually where everything happens and everything is stored. So they do the calculations. That's where Facebook is. That's where Google is. And they are on servers in somewhere else. So that's the basic client-server model. And if we work remotely, so if we request a web page, if we surf the web, if we work on Google Docs, that's all that's all based on the client-server model. So our computer serving as a client, and a server being the servers giving us the information, giving our client, our computer, the information to display. So how does this work exactly? Well, first of all, you have a number of network devices. So you have a number of devices that make sure that computers can communicate with each other, which is basically the hardware. So it consists of a number of cables connecting the devices, and it consists of devices. So you have devices which you use to access a network, your Wi-Fi, the Wi-Fi module in your computer, the 4G, 5G model in your computer, the Bluetooth in your computer. Those are all tiny bits of hardware that connect your computer to a network. Then you have interconnection devices that are computers that can connect one part of the network to other parts of the networks. Things like routers. So you have your own home network consisting of all the computers that are connected via Wi-Fi in your home. And that smaller network is connected to the outside world, to other networks via a router. It can also be via a hub or a switch. That's not that important. So you have multiple types of devices. And what you see more and more now is that we have kind of a mesh network in which you have, which is kind of in between interconnection and access devices, which allows you to create a network on the fly. So when you get a new KPN subscription, you get a mesh network. Google Home is a mesh network. But basically, it's a network and a connection device in one, which makes sure that all of your devices can be connected to one larger network. That's called a mesh network. And the internet basically consists of billions and billions and billions of these network devices and the computers that connect them. Sorry, other way around. Billions and billions of the computers and the billions of devices that connect those computers. That's what the internet is. The internet is not something, it's not some ungraspable thing. The internet is nothing more than billions of computers connected to each other. That's it. But made possible by a lot of different agreements. So the internet is basically a large-scale computer network connected of billions of connected devices. It used to be computers only, but now you have webcams, doorbells, thermostats, phones, many different devices connected via the internet. I'll come back to the question in a minute. So they're connected in a mesh network, and a mesh network means that it's kind of a spider web. So basically, if one connection in the spider web fails, you still can get through other connections via a different part of the network. So simply put, if someone cuts a cable in the Atlantic Oceans, there are lots of other cables still there to keep the connection going. And that's a mesh network. And that's actually the origin of the internet. So this is the internet in 1980. Made by the Department of originally created by the Department of Defense in order to connect strategic locations in the US to each other. Before the internet, it was just done by one-on-one location. So that's one connection between two locations with one physical cable. But then if the Russians would bomb the US with nuclear missiles, then they would bomb, well, somewhere here, New York, and then some of these nodes, some of these connections, of course, would go down. But if you have a mesh network, if one of them fails, you can still reach all of the other locations via another route. And that proved to be very handy in building a network, and that's what has turned into the internet that we know now. So it doesn't always run that smoothly. So I remember that a couple of years ago, a shipping vessel accidentally cut a cable with a fishing net in the Indian Ocean. And as a result, I think almost the entirety of India lost the internet connection because all the traffic suddenly had to go to only, I think, 1 or 2 cables remaining. And those were just too small. They had too small bandwidth to connect, to be able to get all the information across. So you still have physical issues, but with a mesh network, with a web, as it's called as well, of course, the great advantage is that you can really have multiple connections between different parts of the network. So that's where you get to your question. So depending on the activity you do not actually connect to a different network, because everything you do is via the internet and usually via the World Wide Web. But it just ends up in a different location. So of course, there's all kind of security layers, so no one can access the information. So it's encrypted. But basically, all the information you send, so everything we do right now, is sent through the internet, through the World Wide Web, and then is sent to a specific other computer. So I am a specific computer I am in front of a specific computer right now. That computer has a number. My computer, the number of my computer is currently connected via the internet to the computer at Zoom, or computers at Zoom, and you are connected as well. So when I talk, very quickly, the signals are transmitted to the central servers of Zoom, and they transmit it back via the World Wide Web to your computer via the internet. You can make it a bit more complicated because there are ways to have a secure one-on-one connection between two different locations. That's called a virtual private network. And that's what you do when you log into the university's network in order to search for literature, for example. So then you get a one-on-one connection between your computer and the university's network, so that for the outside world, you're just part of one network. And that's much more secure than sending information across the World Wide Web. Or that's a bit too advanced. So what we call the internet is basically just the physical structure of all the interconnected computers. The internet is not only the World Wide Web, so it's not only web browsers. So that's the most used part of the internet, but it's not the only part. So we also have email, we have file transfer protocol, we have chat protocols, we have protocols that you use to play games with each other, which can be, I think, UDP or something like that. And those are all parts of the internet that are not part of the World Wide Web. So we usually say the internet when we browse the web, but when we browse the web, we actually use the World Wide Web. And when you use Google Docs or Facebook, you also use the World Wide Web part of the internet. But it has other parts as well. So the internet is the physical structure, and on top of the physical structure, we have the World Wide Web and other applications. So it uses TCP/IP as the main communication protocol. I'll get to that. So all of this is, all of the internet we have is basically made possible mostly by people agreeing on stuff. So it may sound weird, but actually the whole internet and how it works is, for the larger part, not really technical. It's just based on a bunch of agreements between people and organizations of how we should communicate with each other. So it's really protocols and standards that are the backbone of the internet, and also hardware and software as well, by the way. And a protocol is basically a standard way, an agreement of how systems and computers should talk to each other. And a very simple example of a protocol and a standard is Unicode and its precursor ASCII. So that's a standard agreement of how our characters that we write with, or how our alphabet is represented as ones and zeros. For example, the number 65 in binary it would be 1 on the 64. Well, it would be a bunch of zeros and ones together, and that bunch of zeros and ones together in binary is what we have defined as the capital letter A. And in base 10, in the way we count, it's the number 65. So 65 is A, 66 is the capital letter B, etc. So if a computer gets sent a signal 65 together with the information that that is a character on screen, the computer outputs a capital A. And that's not necessarily a technical thing, but that's only because we agreed that 65 is the capital A. And that's also how emojis work. So emojis work in exactly the same way. So emojis are part of Unicode, so are part of the huge code, which consists of, I think, 150,000 different numbers with symbols attached to them. So a basic smiley in Unicode is U plus 1 F600. So that's another way of representing a list of zeros and ones. So an emoji is just a code of, I think, 16 or 32. I don't remember, but I think 32 zeros and ones. And then there's a huge table, and the computer simply looks up, okay, this list of number and ones, that's a smiley, and then it outputs a smiley. So basically, when you enter a smiley or another emoji in your WhatsApp conversation, that smiley gets translated into the bunch of zeros and ones. Then it gets sent to another phone. Then the other phone knows, because of the table, okay, this code is that smiley, and then it outputs that smiley or that emoji. And that's also the reason why emojis don't look the same across platforms. So the emoji on a Samsung phone is different from the emoji on an Apple phone. They all have the same code, only how they specifically translate that code into the smiley, so how they laid out the smiley, can be different across platforms. But they all know that code U plus 1 F600 is a basic smiley. So instead of sending someone a heart, you can also send him or her a code U plus 1 and then something else. And that is only made possible because there are a bunch of people who come together every year and agree upon the codes that are attached to certain characters. And that's a protocol. And the whole internet works like that. It's based on all those protocols. So every now and then, a bunch of people from different organizations, from IBM and Google and Microsoft, they come together and they discuss how the internet should work. So they discuss, okay, what happens if we send a package? No, I send regular emoticons, but I don't know those numbers by heart, and she doesn't. She doesn't as well. It would be fun. Let me look it up for you. So this is the full emoji list. It's kind of extensive, of course. Do we have a heart? Heart. No. Here it is. So you can send the following code, U plus 2665, to your girlfriend, and that would be a heart. Oh, that's not the correct one, I think. But, yeah, who keeps track of that? Well, there is a work group. So Unicode. Unicode is the central organization who keeps track of all the symbols in the Unicode protocol. And it's not only emojis, it's also our alphabet, it's the Chinese alphabet, it's the Greek alphabet, it's periods, punctuation marks, etc. It's everything. So they are the organization who keeps track of that, and they have different work groups who work on different parts of Unicode. So you have an emoji work group within Unicode. They come together each year to discuss the emojis. So which one should we kick out? Which one should we add? And if you if you want to submit an emoji, you can. So you can just, I don't know exactly where, but there should be somewhere on this side. So if you have a good idea for a new emoji, you can just submit it to the work group and they will discuss it. If enough people think that's also a good idea, and if enough people think that's a good idea for a new emoji, the emoji gets entered into Unicode and it will be added to the next version of your mobile software. And now most of the information systems that work with outputting something to humans work with Unicode. So if you, I'm not sure if it's still here, but in Notepad, you used to be able, here it is. So I can specifically choose the type, so you have different Unicode implementations. I can choose the specific protocol for encoding my Notepad file into Unicode, so into the list of zeros and ones. So UTF-8, Unicode version 8, is the standard way, but you can also pick other ones. Don't touch this is all technical stuff. But even something simple like Notepad in Word or in Windows uses Unicode. But also the way the internet functions. So, so the way that, so for example, when you request a page on the internet, that page on the internet is split up into smaller packages. Then those smaller packages are sent to your computer, and they are combined again, and then you see the page on your screen. So so that's also a protocol. So there is a committee who well, that's here. So there's a committee who talks about how this protocol should function, and they have determined that it should function like that. And you probably heard of a thing called TCP/IP, and you heard that the internet works with TCP/IP. But what that basically means is that the P's in those TCP/IP stand for protocol. So TCP means transmission control protocol, IP means information protocol, and those are two general agreements on how information should flow from one computer to another computer. So what the TCP protocol does, it is a way to split information up into smaller packages of a few kilobytes. And I think IP is Internet Protocol. So it's a way to split information up into separate packages and send it somewhere else. So TCP basically means, okay, if you now see this picture on screen, this picture on screen is sent to your computer, but it's actually broken up into several thousands of smaller packages, each containing part of the image you see on screen. And they get sent through the internet to your computer. And once they have all arrived at your computer, they're combined into one image, which is then displayed on screen. You know, this all happens very, very, very quickly. So it can do it basically in real time. So you know, your computer receives tens of thousands of these packages each second and combines them on the fly into one image. So even as quickly as a moving image. But you may see if you have a slower internet connection, and if I do this, that it gets a bit buggy and a bit pixely, and that's because the computer is not able to send all those packages simultaneously. So you get bandwidth issues. So TCP means a way of breaking it up and combining it again. So basically, if I want to communicate a package, it gets an image, it gets split up into packages. At each of those packages, a code is attached, because of course you need to have a way to get those packages back together. So a code is attached to each package, and based on that code that is attached to each package, the computer can combine all these packages back into one. And the way that that code function is just an agreement. So the people who work on the TCP protocol, they just have made a protocol that says, okay, we add a code of, I think, 32 ones and zeros to each package. And the first 16 is to identify the package. The second 8 are to identify the user or whatever. So a computer can put it all together. Well, TCP is more like, so public transport is really the physical aspect, but TCP would be, okay, so for example, if you want to, so imagine you have a football game, and you have a game not on your location. So you, as a couple of thousands of football fans, go to the other stadium. So a bunch of buses arrive. So you have like 100 buses, and each bus contains a bunch of people. And each bus may take a different route, but they all end up in the same at the same stadium, and they all end up together as the full audience in that stadium. And you all know that they're there because they're all wearing the same shirt of the football club they're supporting. So that's maybe a better analogy. So TCP basically splits up the whole audience into different parts, transmits them via different routes if they have to the same location, and then combines them back into one. So that's, thank you, because that's, I think, a very good analogy of how TCP works. Then using that same analogy, the IP protocol is a way of knowing where the package should go. So TCP splits it up, brings it back together. IP means where should it go? And IP is basically also a protocol, and IP is, okay, what we are going to do is we're going to give every device that is connected to the internet a different code, so a different IP code. And because we have given every device connected to the internet a different code, we know where to send the package to. So my computer has an IP address, your computer has an IP address, and the computer knows, because it attaches a bunch of ones and zeros to each package, it knows where that package should go. And it not only knows where that package should go, it also knows the route it should take. Well, it doesn't know it by heart, but it can estimate where it should go. So for example, take into account the Zoom conversation. So first, the packages that make up this presentation go to Zoom, and then they go back again to your computer. But there's no direct connection to Zoom. So first of all, my packages go to my router, and then from the router, they go to my internet service provider. Then the internet service provider sends it onwards to Zoom, but it probably first goes to the Amsterdam Internet Exchange, which is a huge, huge building in which a lot of different internet traffic is handled. Then they probably send it through the Atlantic Ocean through a cable. Then somewhere in New York, it pops up again. Or maybe Zoom servers are in Ireland, I don't know. It just goes through a lot of different locations. Yeah, you can actually track the route. So you don't necessarily need a separate location. I can do it for you. So if I access, so let's access IBM.com. So I can do trace root IBM.com. Takes a while. Sorry. Gosh, it's slow. So what you see here on screen is the route that my computer takes to the server where the website of IBM.com is stored. It's a bit slow at the moment. Sorry about that, probably because I have lots of other connections going on. But the package is first sent to kpn.home, then it's sent to 2 other KPNs. Then it goes to Euro rings, probably some central location somewhere in Europe. Now it has gone to the UK. I have no clue where this address is, but probably in the UK, maybe in the US. So here you can see how my package is sent through the internet to the other location. Maybe it goes quicker if I do the Dutch address. No, I don't have the patience, but you can see the route here that my computer takes, and you can also see the address my computer has. Config. So this is the IP address my computer has in my the IP address that my computer currently has in my home network. And my outside IP address is then something else, which I probably is best if I not show this on YouTube. So that's how the internet works. So it's basically built upon these 2 different protocols. So the internet protocol and the IP protocol. And that's basically what makes the whole internet happen. Then there may be some other abbreviations that you would like to know, which is basically more from the world, results from the World Wide Web, from when we browse websites. So of course you all know what a URL is. So a URL is just a website address. So www.uvt.nl is the website address of the University of Tilburg University. But a computer doesn't know that. So the computer doesn't know what Tilburg University is. So similar to Unicode, there is a huge table that contains the IP address of the computer and the URL name. So when I type in www.uvt.nl in my browser, my browser sends www.uvt.nl to a domain name system server, a DNS server. That one has a huge table which knows www.uvt.nl is this IP address. And then it translates that back into a number. And that's the number, that's the bunch of zeros and ones that a computer can understand. So if I type in the university address of Tilburg University, I know that this IP address 137. etc. That's the actual code that is assigned to uvt.nl. So, and I think that if I type this one into Google or into here, if everything goes well, I should also get the maybe it's this one. I'm not sure why my computer is so slow right now. Probably because Zoom is taking up a lot of the bandwidth. Well, never mind. if you type in the correct IP address, then you also get to the website of the location where you want to be, because the URL is just a code. We could also learn a lot of DNSs by heart, but for us it's easier to remember a website address, and that's why we have the domain name system. Well, then to conclude, HTTPS is the protocol that is used to display, so to communicate between web browsers, and then we have a bunch of different languages which are built to display pages on your web browser. But it's all based on protocols and all based on standards that together make this happen. So for the course, I think it's important to remember what TCP/IP URL is, and HTTPS as well, but you don't have to learn how to, so the language protocols and how HTML work. But this, I think is basic knowledge that helps you to understand a lot about how the internet actually works. So to give you an example of HTML, this is actually how an internet, a very simple internet page is coded. So if you paste this, so if you would request a page like this, your browser would display it as a page, but the actual code to write it is this. So this is how, it's called hypertext markup language. It defines how browsers should display a web page on screen. And still, if you go anywhere online, so this is the source code of the website of Tilburg University. So this is how you code how to display the page. It's useful if you have free time and if you are interested in learning about basic website building, then HTML is the first thing you should learn. It's quite simple. So this looks pretty complicated, but actually the basics of HTML is very, very simple to learn. So if you're interested in more the technical aspects and how websites work and function, this is something that's really helpful to learn. Also, if you're interested in social media marketing and social media analytics, it's good to know a bit about HTML and how websites are displayed. I'll just skip this one. So that's actually the main thing I wanted to explain about hardware and software. So a bit of knowledge about how a computer works, a small bit as well about how the internet works, to have you get a bit of a grasp about how this all works, and to give you a bit of a feeling of what is involved, and how many people have worked on making it possible for us to use Facebook and WhatsApp and having this lecture using Zoom. Finally, I want to just quickly talk about two trends in organizations, which I think you will learn a lot about and hear a lot about when you start working. So one of them is that what I was talking about, the client-server models and about how organization works. You see that is changing in organizations, because increasingly it's kind of bring your own device and mobile technology that we see happening in organizations. So it used to be the case that everyone in an organization had a desktop computer, you use that and that was it. But you now increasingly see that people get a laptop from your organization or use their own laptop or use their own phone. So there is more and more integration of mobile devices and devices that come from outside of the organization that have to be used within the organization. So the whole shift to mobile technology and bring your own device, I think it's pretty interesting from a technology and IT point of view, because of course it brings about all kinds of issues with security. So you have to do like virtual private networking or fingerprint authentication in order to make sure that your network stays safe. So if you look within IT departments, so this is one thing that IT departments themselves are working on right now. So that's one. And the other technology trend is cloud computing. So you increasingly see that more and more and more of the IT functions of an organization are outsourced somewhere else. So for example, your university account is actually a Gmail account. So it's actually done and arranged and dealt with by Google. We are shifting towards the use of Office 365 in the university. So they just released the first version of it for employees to use, which basically means that all of the computer programs we work with, all of our storage of our documents is all done by Microsoft. So we need little internal or corporate network anymore. So we don't need servers in our university to store our own documents. We just use Microsoft as service. And cloud has shown, so everyone knows cloud software, you know, everything we do is in the cloud, you know, Twitter, Facebook, Instagram, WhatsApp, Google Drive, Google Docs, Office 365, even most enterprise software nowadays, Microsoft Dynamics, SAP, is all done in the cloud. Netflix as well, of course. So cloud computing is huge as well. So it basically means, cloud computer basically means that things we traditionally do with information technology within our organization, we do it outside of the organization. So we outsource it. So you can outsource software, you can outsource storage, you can even outsource the computers themselves with, so you can outsource the servers, but you can even outsource contracts for maintenance. So that's the second big trend you observe in organizational IT departments, that more and more is outsourced. I think it's pretty interesting to conclude, because on the one hand, it has huge advantages, you know, so you don't have to do it yourself, so you don't have to retain the knowledge. It's usually less expensive. You only pay for what you use. Security is dealt with somewhere else. You can automatic upgrade. So it has a lot of advantages, but it also has a lot of risks. So if you lose your internet connection, no one can work in your organization. So it also results in loss of knowledge. So if you outsource everything IT, how do you innovate? So you may lose valuable knowledge within your organization. So I think the outsourcing part and cloud computing is very interesting from a business perspective, innovation perspective as well, because the more you outsource, the less technical knowledge you have in-house, and maybe the less able you are to innovate as an organization. So I think if you are an organization, especially one who depends on technological innovation, you should not outsource everything. So you should be very careful about what you do yourself and how innovative you remain yourself and what you outsource. But I think that goes a bit too far for this course and this explanation. So that was it. I want to thank you very much for the ones who are here. I hope this has given you a bit of understanding in how computers and networks work. So thank you very much, and good luck with the course, and I'll see you next Monday, whenever you view this. Thank you.